Peter Bruza about probabilistic programs.
So the talk today is going to follow on some of the other talks. In particular, I'd like to sort of try to bring together two frameworks that have been used to express contextuality. There's Eddie and his colleagues, contextuality by default, and also it's also been mentioned a couple of times, Sampson and Bransky's approach. The way I'm going to try and do it is do it in the context of probabilistic programs, and the whole idea of these probabilistic programs are that it would be a convenient way for probabilistic modelers to develop models, and just like computer programs, these programs would execute. And if there is contextuality present, then contextual semantics would take hold. And if there's no contextuality, then the program would run according to standard probability theory. So that's the ultimate goal. So I'd like to start with a motivating example here. Maybe you can't see that, but this is a schematic of a programming language called Fortran that was developed from the late 50s to 60s. And what you see here is there are a number of different variables declared, and there's a certain function that's going to use the variable x in order to compute a value. Now, in those early programming languages, all the variables were global, so this could be a source of errors. So, for example, here we see a variable x has been assigned a value, and in the middle of the function, the programmer has inadvertently forgotten, maybe because it's a very, very long function, that this variable was used as an input parameter, and they've overridden it by another value. So the problem that here is that the variables become overloaded. In other words, and what I mean by that, it's being used for two different functions in the program, and then it causes an error or a bug. Now, there is an easy way to fix that. And what you do is you essentially you divide the random variable x into two variables, x1 and x2. So x1 is used for its original purpose as an input parameter, and in here x2 maybe there's some local computation that's being used in the context of the function, and so that you split the variable up, and this way you keep the distinct purposes disparate and complete. So in this way, this fix is very similar to the intuition that Eddie shared earlier about in contextuality by default, is that when we have a random variable, it's indexed or tagged by all conditions in which its realizations are recorded. Okay, so this is so all I'm saying is this is very, very similar to what was happening in the field of programming languages. Now, the question that you could ask is whether this overloading is happening in the area of probabilistic models developed, for example, in cognition. And this is a diagram that's been taken out of one of the papers of one of my colleagues who does a lot of Bayesian modeling. And this model is about cheetah populations. And you can see that there are three different contexts here. There's a humans factors context. You can imagine how cheetahs are interacting with human beings. There is an ecological or environmental context, and then there is another one here, which is the biological context. So the whole idea is that different modelers would come up with a probabilistic model for each of these contexts. But you can see here this variable cheetah removal, which is up here, is also present here and also down here. So even though it's not definitive, it's easy to see that it could be an underlying assumption that this variable cheetah removal in this context is the same as this variable in this context is available in this context. But I think the difference that you would have between the programming language example that I gave before and the probabilistic models is if you overload the variable in a program, then the error becomes apparent fairly quickly. But when you're doing probabilistic models, it's maybe not so clear that there are some errors occurring or some bugs occurring in your models. So maybe this overloading of variables in probabilistic models is actually a much more subtle thing to to do and harder to notice the ramifications of. So, sorry about this, I'm going around the wrong way. So now I'm going to get to the motivation of the talk. And this is, it starts with a question that I've been sharing with a colleague, Kirsty Kiddo in Australia, is we've asked this question whether the way we develop probabilistic models now is similar to what was happening with Fortran and this programming language, where we have these variables that are always global, they're always globally accessible. And so what we're trying to do is trying to come up with a probability theory where the variables aren't always globally accessible. And the problem, so one way to do this is just been given by the Contextuality by default talk, is that we record all the variables under the conditions in which it was recorded. But it's easy to imagine that in large modelling situations, for example in big data, that it might be inconvenient for the modeler to always subscript the variables across all the different contexts in which it is being recorded. So the idea would be to actually develop a language which will make this a little bit more convenient for the modeler to do that, whereas that the underlying semantics would take into account that certain variables are in different contexts, and you can safely overload the variables like you can in programming languages. So I'll give an example of that now. This is an example of a scoped programming language. And what you can do is you have a global program, and you can declare the global variables, but within that you can declare different contexts. And here you see a variable t that's declared local to this context x1, and you have another variable t that's declared local to the variable x2. So the whole idea is that it might be convenient for the modeler to overload the variable, but it's the actual syntax of the program that will allow you to, that will take into account that these variables are different, and so you won't get a bug in the program. And another facet of this program is this thing down the bottom, is this syntax here called a p-join. And the idea is that different contexts return a given probabilistic model. So if you have different contexts in your program, the whole idea is that you want to be able to join these different models into a single model which will return as the final result of the program. So the question is how to form a single model as a final result from these interim results. So this is where I'm going to draw on some of the ideas of Samson and Bramstein. So he's developed these contextual semantics, and this is based on sheaf theory. And the basic idea behind that is that you have some things called local sections, which are represented by these little circles here of two different colours. And the whole idea is the question is whether you can join these local sections into a global section. And if it's possible to do that, then you have a system that is non-contextual. If there is no glue that can do that, there's no glue that's present in order to achieve the global section, then the system is deemed to be contextual. Now, one of the things that Samson did was be able to show that this particular sort of abstract definition of the problem is present in a number of different contexts. And as he's got a background in computer science, he noticed that in the 1980s there was this problem when relational databases were being developed, that you have a database that contains a number of different tables. So for example, here we've got a customer table, here we've got a transaction table, and here we've got a product table. And the problem was how to actually join these tables together into one single table such that we can recover each of the individual tables by projection. So this is very similar to the way it's framed in probability theory, is that if we have a number of empirically collected distributions, for example in an EPR experiment, can we come up with one single distribution from these four pairwise distributions such that we can recover the empirical distributions via marginalisation. So it's an equivalent problem. So it just shows in the early 1980s that this question was being actively looked at. Now, in Sampson's work, he's been using these things called probability tables, and this is an example of one from an EPR experiment where at the top you've got some joint events. Down the left-hand side, each row represents a particular measurement context, and each row corresponds to a probability distribution. Now, what we did was we tried to run with this intuition so that there is this problem in relational database theory about trying to construct this universal relation or not. So why not just try and use relational database theory as it is and see how far that gets you? So rather than use a probability table that Sampson uses in these contextual semantics, I took the most basic step is that you take a table in a relational database and you make it probabilistic. So this is an example of such a probabilistic table. So you've got two dichotomous random variables, and these are the probabilities that all sum to 1. So if you have that, then the question then, what do you do in terms of the glue? So the whole idea is that you have these p-tables, and then you need to be able to glue these together and to try and come up with a single model that is the final result of the program. So here are some examples of some glue. So the approach we took was probably the most basic glue that is offered by relational database theory. So here we've got two probabilistic tables, X and Y. And there's one form of glue is a Cartesian product. And what that does is essentially you take every row from the left-hand table X and you join it with every row on the other table, and so that you get all combinations. And you simply cross-multiply the probabilities. And notice that when you do this, when you form the Cartesian product, you actually then have to sort of rename the variables here, because there's T in both these tables, into T1 and T2. So there are databases like database languages like SQL that actually automatically do this renaming behind the scenes. So this would be one of the ways in which you could get the programming semantics to actually do the automatic renaming that is suggested by the contextuality by the default principle. Another form of glue is the natural join in relational database theory, and this is probably one of the most common ways of joining tables together. So in many applications in relational databases, you're trying to pull information together from different tables. And so the whole idea of the relational join is that you essentially zip up the table across the common variable. So in this example here, the attribute T is common to both tables. So you use that value in the T column to join this row with this row, because they've both got the value 1. So similarly, you do that all the way through all combinations. So you get the table essentially zipped together across the values of the attribute T, and then you actually then the numerators you multiply the probabilities as in the Cartesian product. But then you actually have to divide that by the marginal probability of T. So it only makes sense to do the natural join if the marginal probability of T is stable across both tables. Otherwise, it doesn't make any sense. It's not well defined. Now, so let's take an example. And here are two P programs, and they are meant to model an EPR experiment. So in an EPR experiment, you have 4 different contexts. So this is context 1, context 2, context 3, context 4. So you'd have the A1, B1 context, A1, B2, A2, B1, and A2, B2. So the only difference between these programs is that this is the EPR program here, but in this case, the program has a variable A3, and in this one here is a variable A2. So you see that the programs are very simple. So what we do is we develop a probability distribution, we read in the data from the experiment, and we return the distribution. So we do that across all the different contexts, P1 to P4. And in the end, the whole idea is that we want to join those distributions together from the different experimental contexts in the EPR experiment. So this is the standard EPR. This one here is a different one where we've got a different variable A3 instead of a variable A2. And I'll use this to sort of show how the semantics differ. So on the one extreme, this is the left-hand program. These circles here, they represent the variables that were local to each of the contexts. So in the context of the previous talk by Eddie, these would be the bunches. So here we have A1B1, A2B1, A2B1, A1B2, and A2B2. And the edges represent the variables that are common between those bunches. So essentially this is a hypergraph representation. Now what was done in the relational database theory in the early 80s, they had this theory in order to work out whether the schema of the tables in the join operation was acyclic or not. Because once the schema is acyclic, then it was fairly easy to come up with a join operation to come up with that single universal relation. And so this is what happens in this case here. So you can see that we have an acyclic case, and essentially you can start with P3, and then you can go to P1 to P2 and P4, and then what you get is a generalized acyclic join dependency which has a form like this. And then it's easy from this generalized acyclic join dependency to construct a joint probability distribution that corresponds to the universal relation. And this is essentially what it looks like. I've written it down here. So these are this is the 5 variables that are common across all the different 4 contexts. The numerator consists of the 4 bunches, and you divide that by the marginal probabilities that correspond to the variables that are common to the edges. So this is a straight sort of computation about how to get the joint probability distribution. So this is an expression of the Vorobiev condition, and something that's mentioned in Sampson's article relating contextual semantics to database theory. It's interesting then to contrast the acyclic case with the cyclic one. So this is the 4 cycle we see in the EPR setting. So, and the question here is when you have a hypergraph that's cyclic like that, what you can do. So the computer scientists were looking at this problem, and then as far as I can tell, they never really solved the problem of contextuality as has been done here. So there are a number of different, so in the work that I'm referring to in the paper by Geissens and Paradigms, in certain cyclic cases, what they can do is they can identify hinges in the cyclic hypergraph, break the hinges, and they can break the hypergraph down into an acyclic component and hopefully work from there, and then just combine different acyclic elements. But sometimes there is a cyclic element that can't be broken down. And these were called so-called supercycles, and they never really had a solution for that. So this is an example of one of the supercycles. So when you're using that sort of theory, then the database theory cannot is not diagnostic with respect to contextuality as we've seen earlier today. So what you can do, and this is an example of some operational semantics here, is if you assume that none of the marginals agree. So what you can do here is the semantics, you can use a Cartesian product. This is using the language SQL. So essentially combine all the different component distributions into one distribution where all of the variables are renamed behind the scenes, and that would be the semantics that would be produced by the program. So it's a simplistic solution, but once again, it's not diagnostic with respect to contextuality, unfortunately. So I just wanted to show you, this is some reflections of Dyson's and paradigms. So this is written in the early 1980s. And then they were talking about this, they were looking at this problem, how to come up with a universal relation. And the reason I'm showing this is it's sort of like this, the intuition behind this is very, very similar to the intuition that Eddie was sharing earlier. Was that they said that cyclicity implies that one or more attributes of the database are overloaded. So once again, it gets to this issue of overloading variables. And so the reason why a database attributes such as product might become overloaded is that it has more than one function. It might mean a product is being supplied or a product being purchased. So this is alluding to the fact that even as a database modeler, you're using the one attribute. But this is leading to some problems, and that this prevents you coming up with a universal relation. So with something like, so by nominating the different contexts, it suggests that maybe then, if you kind of come up with an alternative model, you actually should split the variable product into two names, one product being supplied, another product being purchased. And so that would be corresponding to the first principle of CBD that we saw earlier. So just to summarise what we learned from this, so the whole idea is we want to connect contextuality with probabilistic programming by using relational database theory. There were two cases. There is an acyclic schema. So when any of the margins of the p-tables being glued do not agree, then the system's contextually can't come up with the universal relation. So if the marginals across all the edges of the acyclic hypergraph, if they're in agreement, then we can come up with a single probability distribution representing the acyclic hypergraph. And then this would be a non-contextual situation. The other cases, when you've got the cyclic schema, well, currently the semantics can't diagnose contextuality, so that's unfortunate. And it's doubly unfortunate because, as we saw earlier, most of the interesting cases in contextuality deal with cyclicity. So that we haven't got very far using relational database theory. So just some further points. The first principle is contextuality by default. This is where we have to rename variables according to the context in which it's recorded. The whole idea is these probabilistic programs that you would use these syntactic scopes, so you can overload the same variable name, but the semantics will keep in the background will keep these variables distinct, so as the probabilistic modeler doesn't have to worry about renaming. So that could be something for modeling convenience. The similar relational database approach to this gluing, so using Cartesian product and natural join, it doesn't really tell us much about contextuality. And in fact, some of the things we already know about contextuality can't really recover. So clearly the simplistic approach to taking using those two operations doesn't get us very far. I think for further work, I think that there is this issue of stochastic unrelatedness, because when you're developing these probabilistic programs, you can develop these syntactic scopes which correspond to, for example, different experiments that you're conducting. And then these syntactic scopes in programming languages, if you declare a variable local to a scope, that it's not visible to other variables in other scopes. So this has, intuitively, this has the similar intuition to stochastic unrelatedness. So I think it would be interesting to see how this syntactic definition of scopes of variables not being visible to each other across scopes, how that relates to stochastic unrelatedness. And that's it. Thank you for your attention.
Questions, remarks?
Let me
Yes.
add something. Now, according to Dr. Doria, there might be some fundamental problems with establishing contextuality algorithmically. Do you care to speculate about this, like beyond the fact that we cannot actually do it with these programs? Do you think there might be some kind of principal obstacles when you
Well,
come up
then,
with.
well, so the whole idea of these programs, like if we use the contextual semantics or the contextuality by default, this would provide the underlying semantics of the program. So in that sense, the program would function according to the definitions of contextuality that have been set out by you or Samson. So they would adhere to that. So in that sense, I wouldn't see that there's a problem. So maybe I don't fully understand the question, but
Well, maybe I don't understand my question either, but let me just suggest one thing that, when we actually establish contextuality of a system, right, and if all the variables, and it's the same is true about your variables in your programming languages, if they are all categorical, so each has finite number of values,
yeah,
then essentially the computation is a linear programming task. Right?
yeah,
I mean, you are just setting up a linear programming task of, with some modifications,
Yeah.
but essentially, and then you always either get a solution
yeah,
and prove non-contextuality,
yeah.
or you get a definitive answer that there is no solution and that
Yeah.
it's contextual. Now, I have wondered myself whether, this thing is, well, first of all, are you aware of any pitfalls in that? I mean, according to what I know, a linear program always gives the solution in polynomial time, or there are no problems.
Yeah.
Right? And second, what do you think should be done if you go beyond categorical variables? Let's say you have infinite number of values. How would something like this work?
Yeah, well, that's a good question, because if you look at that, like probabilistic programming is a hot topic at the moment. It's been driven by big data. So a lot of the probabilistic programs you see are dealing with non-categorical variables. I really don't know how to deal with that, because this is really opening up the problem space there, and we've got definite challenges there. But I don't see any in principle problems with just extending it to that. At least that's my hope. Or do you?
I don't see why there should be any problem, but
It's
we
the
haven't
same here.
actually done anything algorithmically beyond categorical variables. So,
Yeah.
yeah.
So I don't see any in principle problems.
This might be more of a basis for a lunchtime discussion than a question, but there's a couple of threads in what you said, starting with the two local sections of a sheaf, and can you get a global section, and you've got a couple of variables that might be able to have consistent meanings or might not, and those descriptions start to sound very geometrical. In particular, whether you can get global sections is very indicative of the underlying topology of a space you're working on, and whether you can make different coordinate frames, as in collections of variables that parameterize a surface, consistent with one another, is also very much all about the topology of the underlying space. Is there an underlying space whose topology we should be interested in?
I don't know.
Should we go for lunch?
No, I can't. I don't have any intuitions about that at all. I think that
Yeah.
I think I'm more familiar with Samson's work with the sheaf theoretic framework. That I guess that has a certain that has a topological aspect to it. But I guess the question is whether those the semantics that Samson is producing, or those of Abby, are they actually covering all that we want to be able to cover? are they expressive enough for notions of contextuality that we want to, that we as modelers are confronted with or want to take into consideration? That's a semantic issue, whether such things are well defined enough and whether they're expressive enough. And I guess in this forum we're still, this is an ongoing exploration, I think. There's continuing development in this area. So thus far, I think the amazing thing is that when I talk to probabilistic modelers and I try to explain to them about contextuality, as we've explained here, they don't think it's a problem. They think so. Even there was a Bayesian modeler that was saying, well, we've got this random variable across different contexts, and I said, well, what happens if the marginal is different? Shouldn't that be two variables? No, well, we just use a parameter. So they fix it by introducing a parameter. So by hacking with their models, they can actually then still do what they want to do. But theoretically, it's not so nice. So I think we've got this issue. Like, I've had several discussions with people. Like Bayesianism is rampant at the moment, and unless we convince these people that there is a problem, that there are potential bugs in their models, unless we can be convincing about that, then they'll never listen to us. They'll say we're just developing this weird theory that's perhaps a little bit interesting, but it's of no use. And I think this is the challenge we have as this community, is to actually come up with some really, really good examples where, for example, a Bayesian model has bugs or whatever, or is very, very ugly, whereas and then we can argue that by taking contextuality into account, this new theoretical perspective, that we actually should look at this very, very fundamentally different from a modelling perspective, and just not simply assume that the joint distribution is there. But that's my view on it.
But Bayesian models are ugly, no?
Oh, well, yeah, okay, but ugly or not, they are kicking a lot of goals on the ground. You go to the Cognitive Science Conference, and then so much of it now is being run by, or dominated by Bayesian models. There was an article that came out in, I think, Behaviour, Brain and Methods or something a couple of years ago, that was called Bayesian Fundamentalism. Or enlightenment. And this was reflective that Bayesianism has become almost like a fundamentalist sort of creed within cognitive science, that everyone was jumping on the bandwagon, and this was solving a lot of the problems. And and alternative perspectives are then maybe pushed to the background. And then when you get a situation like that, it's harder to see what the limitations are of the model. And I think this is the one thing I've had several discussions with Jerome Bussmeyer and others about this, to be very, very convincing that that contextuality and these things are very, very important from a modelling perspective. Because when I first came across this idea that the joint distribution doesn't exist, I was shocked, because I developed a lot of probabilistic models, and you write down the random variables, you might come up with a Bayesian network, but you never ask the question, does this distribution exist or not? You just assume that it does, right? And so I think this is similar to the early errors that were made in programming. So that we have these global variables, and then we overload them. And then that leads to problems. But I think at the moment, I think the subtlety here is in probabilistic models, at least used in cognitive psychology, that the effects are more subtle than they are in computer programming, where you can see that the effects of the bug were more dramatic. So then you realise that you had a problem. I don't think they realise they've got a problem. So sorry for that big spiel, but
Okay, thank you very much. So we start precisely at